It's going to be Kun Fang, and he's going to talk about the quantum channel simulation and the channel smooth max information.
Thanks for the introduction, and thanks to the organizer for giving me this opportunity to present here. I will talk about information task called quantum channel simulation and a newly introduced entropy called channel smooth max information. This is based on this archive paper. And it's a joint work with Xin Wang and Mark Tomamincho and Maria Berta. This is the outline of this talk. I'll first introduce some backgrounds of quantum channel and quantum channel simulation. Then I'll go to the main results of this talk. It will involve entropy of a channel. If I have time, I will show you some of the proof outline of the AEP of this new entropy. And finally, I will give a brief summary and the discussions. So let's start from the first part. As a quantum analog of classical channels, a quantum channel is a communication channel which will allow you to transmit quantum information. It sends one quantum state to the other. Mathematically, a quantum channel can be characterized by a linear map that is completely positive and trace preserving. Sometimes we just simply call it CPTP maps. And more intuitively, we can represent a quantum channel shared between A and B in such a box with input system A and output system B. Then the task of channel simulation is that you have quantum channel N, and you need to transform this channel to another channel M. What you can do is to add an encoder at the input side and a decoder at output side. You may also use some shared resources between A and B. So more generally, we can write the operation in this part as a single operation pi. Then the task of channel simulation becomes choosing the optimal operation pi in a set of class operations such that the effective channel, which is the composition of pi and n, behaves as similar as to the target channel n. And this similarity can be measured via diamond norm due to its well-motivated operational meaning. So suppose you have two quantum channels n1 and n2, then the minimum error probability to distinguish these two channels is given by this expression of diamond norm. So the smaller the diamond norm distance between these two channels, the larger error probability you will get. So the harder you can distinguish these two channels. And based on this diamond norm, we can define the minimum error of simulation as the minimum diamond norm distance between the effective channel and the target channel. And the optimization is taken over a set of allowed operations. It depends on which resource you need. And this minimum error characterizes how well you can perform the given channel simulation task. In terms of information theory, we also concern how many copies of the resource channel needed on average to simulate just one copy of the target channel. So suppose you have n copy of the resource channel, which can be used to simulate m copies of target channel. Then the rate is given by n over m, and we want this rate as small as possible. During the simulation process, different resource systems can be considered. And in this talk, I will focus on entanglement systems, which means A and B can share any entangled state, and non-singular systems, which is a more powerful correlation containing any operation pi such that A cannot signal to B and vice versa. By saying A cannot signal to B, I mean the output state of the B prime system is independent of the input of the A prime system, and this also works for the not signaling from B not signal to A. And it's very clear that non-singular systems is a more powerful system than entanglement systems in general. This quantum channel is used to transmit quantum information faithfully, and the most faithful channel is given by the identity channel. So regarding to identity channel, there are two special cases of channel simulation problems. The first one is to use the noise channel to simulate identity channel. This is equivalent to the channel capacity problem, and the optimal rate is so-called channel capacity. In the framework of channel simulation, the channel capacity is given by the inverse of the channel simulation rate. On the other direction, we can also use identity channel to simulate a noisy channel, and the optimal simulation rate is called channel simulation cost. This is analogous to the entanglement distillation and entanglement dilution in the entanglement theory. So operationally, we will have a chain of inequality like this, which says the entanglement assisted quantum capacity is no greater than the non-singling assisted quantum capacity, which is no greater than the non-singling assisted simulation cost, which is no greater than the entanglement assisted simulation cost. And the first and last inequality holds simply because non-singular correlation is a more powerful correlation than entanglement assistance, and the second one holds by definition. And in terms of these four quantities, there are a few more things worth mentioning. The first one is that the entanglement assisted quantum capacity has a single letter formula given by the channel's mutual information, which is given by the maximum mutual information of the channel's output state, and the maximization is taken over all the pure state. And it has also been proved that the channel simulation cost is equal to the channel capacity on the entanglement assistant. So eventually these four quantities are all the same, are all given by the channel's mutual information. And this is so-called quantum reverse channel theorem. It has been mentioned in the last talk. And this result has won the IEEE Information Theory Society paper award last year. So far, I've introduced the background of quantum channel simulation, and well, most of the prior results are focused on the asymptotic simulation cost. We will study the channel simulation task in the one-shot setting, especially using the identity channel to simulate a noisy one with no signaling assistance. And this is the identity channel with dimension n. We'll also introduce a naturally appeared entropy of a channel and explain its operational meaning as well as asymptotic equipartition properties. Let's recall that the minimum error of simulation is defined as the minimum diagonal distance between the effective channel and the target channel. Then we can define the one-shot quantum simulation cost as the minimum dimension of the identity channel needed to simulate the target channel n within epsilon error. Then the asymptotic quantum simulation cost is given by this regularization form. Our first result shows that the minimum error can be given by a semi-definite program, which makes it easy to compute numerically. To those who are not familiar with semi-definite program, you can just simply take it as a generalization of linear program. Here I mark the operator variables in red, so you can see both of the objective function and the constraints are all linear with respect to the operator variables. To obtain this result, we only need to note a few things in the definition. The first one is that our operation pi is not singly if and only if its Choi matrix satisfies these semi-definite conditions. The first two constraints represent the CP and TP conditions, and the last two constraints represent the non-singling from A to B and non-singling from B to A. And also the diagonal distance between two quantum channels can also be written as a semi-definite program. Combining these two facts with the symmetry of the identity channel, we will obtain an SDP like this. And based on this SDP, we can also show that the one-shot epsilon error quantum simulation cost is also given by our SDP. And this one will reduce to the zero error case if we take the epsilon equal to 0. which was studied by Duan and Winter in 2016, they have showed that the zero-error simulation course is given by the conditional mean entropy of the channel's Choi matrix. Then a later question would ask, is this correlation holds for the non-zero error case? Is the one-shot epsilon error simulation course equal to the smooth conditional mean entropy? But after a quick thought, we will know this is not true. Since the left-hand side will converge to the asymptotic simulation course, which is given by the channel symmetry information. But on the right-hand side, the AP of the smooth conditional mean entropy will tell us it will converge to the conditional entropy of the channel's Choi matrix. And we know these two guys are not the same. So to better characterize the one-shot epsilon error simulation course, we will need an entropy that looks more similar to the channel symmetry information rather than the conditional entropy. So let's first review how this was done for quantum states. The max information of a quantum state can be defined like this, which is very similar to the definition of quantum mutual information by replacing the relative entropy with the max relative entropy. And there are several different other variations in the literature depending on different marginal states in the second term, and this is the one we use here. Rho A is the marginal state of rho AB, and we optimize over all the quantum states on the B system. It also has a smooth version, which means we optimize over all the quantum states that are epsilon close to the state considered. And it's known that the smooth max information of the states will converge to the quantum mutual information in the asymptotic limit. So the smooth max information can be taken as a one-shot generalization of the quantum mutual information. And equation like this is called asymptotic equipartition property, or AEP. Then in the following, we will generalize all of these notations and results to a channel version and find their connection with the quantum channel simulation task. For any quantum channel n, we can define the max information of this channel as the max information of the channel's Choi state. And here phi is the normalized maximum entangled state. And we can actually replace these states to any pure state with symmetry rank equal to the dimension of the input system. So no matter, so this definition does not depend on the input, state you choose. And the smooth version is similarly defined for as for quantum states. Since our object here is the quantum channels, so we optimize over all the CPTP maps that are epsilon close to the channel you considered. And then we can first show that this new entropy of channel is monotone on the composition with CPTP maps. More specifically, if you compose a CPTP map before and after the channel, it will reduce the channel's entropy. This is analogous to the data processing inequality for quantum states. In terms of resource theory perspectives, we will have different approach to understand the channel's max information defined. If we define the max relative entropy between two quantum channels as the max relative entropy of these two channels' Choi matrix, then the max information of this channel is actually given by the minimum distance between the channel n and the set of constant channels. And here the distance measure is given by this max relative entropy. And by constant channel, I mean which is a CPTP map. It maps any input state to a constant state. And since max relative entropy is closely related to the robustness of quantum states, which was studied by Jana in 2009, and here we can also do the same thing for quantum channels. So the robustness of quantum channel characterize how much perturbation you need to make the channel useless. So it is defined as the minimum mixture of another channel to make this channel n belongs to the set of constant channels, and we take the infimum of the coefficient t. Then we can show the max information of this channel is actually equal to the logarithm of the robustness of the channel. There's another talk tomorrow by Ziwen. He will show more general results about quantum reverse theorem for quantum channels. And also, here's the operational meaning of this new entropy. We can show that the smooth max information of the channel is actually exactly equal to the one-shot quantum simulation cost. This can be proved by using the SDP characterization of this one-shot rate and the definition of the channel smooth max information. And from here, you can easily see that the monotone of this entropy can be explained as if you compose another channel before and after this channel n, it will make this channel n more noisy. So you will need less resource to simulate this channel. So the simulation rate will be smaller. This is compatible with our intuition. And based on this operational meaning, we can also show that the AP of the channel smooth max information holds, which means the channel smooth max information will converge to the channel symmetry information in the asymptotic limit. So this entropy of channel is a one-shot generalization of the channel symmetry information. And there are different methods to prove these results. And one of the most straightforward one is to use the quantum reverse Shannon theorem. So more specifically, if we take the regularization on both sides of this equation, then the right-hand side will equal to the asymptotic rate. And by quantum reverse Shannon theorem, this is equal to the entanglement C quantum capacity, which is given by the channel symmetry information, which completes the proof. And also, on the other hand, if we can prove this AEP directly, we will partially recover the quantum reverse Shannon theorem. So the quantum reverse Shannon theorem tells that the first quantity and the last quantity are equal. Then it will imply all of these quantities are equal. But the proof of AEP, we can recover the first two equalities. In the next few slides, I will show you the outline of this direct proof. It will be slightly technical. Let's start from the easy direction. So we first write down the definition of the channel smooth max information, and we choose the input state here as the optimal state in the channel symmetry information. Then, since max relative entropy is no smaller than the relative entropy, we know that the max information is no smaller than the quantum mutual information. Then, by the continuity of the quantum mutual information, we can replace the tiered channel here to the tensor product channel, since they're epsilon close. And then this quantity will become the quantum mutual information of this tensor product state. And since quantum mutual information is additive, so it's equal to the n times of the quantum mutual information of this state. And since the input state is chosen as the optimal state in the channel symmetry information, so this one also holds. As for the other direction, we will use the post-selection technique, which also has been mentioned in the last talk. In the definition of diamond norm, we need to optimize over all the input states. But the post-selection technique tells that you only need to check one particular quantum state. If the output state of these two channels are close, then it will imply that these two channels are close in the diamond norm. And here, this particular state is the purification of the definite state, which was introduced as the mixture of all the tensor product pure state. And we can also assume that the dimension of the purification system is only polynomially large. Okay. Based on this post-selection technique, we will be ready to prove the other direction of this AEP. We also first write down the definition of the channel smooth max information. Here we choose the input states as the purification of the definite state. Then we can replace this channel smoothing with the smoothing of these two output states. And if we denote the output state of the tilde channel as sigma, we will have the smoothing over all the quantum states sigma, but with the additional constraint that the marginal state on the reference system is unchanged. The reason we have this additional constraint is because the tilde channel only acts on the input system A prime and leave the reference system AR unchanged. So we have this additional constraint. And then there's a result by Anshu Berta, Jen, and Thomas Mitchell, which will be presented on Thursday morning by Mario. They can show that get rid of these marginal state conditions will not change the optimum value too much. So we will finally arrive at the standard definition of the max information for quantum states. And then in the following, we will just use some well-established properties of this entropy. The first step is to get rid of the purification system. Then the input state will become the definite state, which was introduced as the mixture of the tensor product state. And then by quasi-convexity, we can show this will no smaller than the maximum one. Then the input state will become the tensor product state. And then by using the AEP for quantum states of this entropy, it will no larger than the n times of the quantum mutual information of this state. And by definition, this is exactly equal to n times of the channel's mutual information. And this completes the whole proof. So, any questions so far? Okay. To give you a more intuitive feeling of the AEP, I show you an example of depolarizing channel, which maps any quantum states to the complexly mixed states with probability P, and with the rest of probability, it keeps the quantum state unchanged. And this channel has the same symmetry as for identity channels. So we can simplify the SDP for the unshort quantum simulation course as a linear program. And then we implement this linear program numerically, we'll obtain a plot like this. This blue straight line is the entanglement-assisted quantum capacity, which is also the channel's mutual information. And these three curves will converge to the channel's mutual information in the asymptotic limit from above. And there's another similar plot in this one, which was given by Marshall and Werner. They have given a converse bound for n-short entanglement assisted quantum capacity, and their converse bound can be actually written as the hypothesis channel divergence of the channel n with respect to the set of constant channels. And they have also shown that their bound is asymptotic tight. It will converge to the channel's mutual information. And the straight line here is also the channel's mutual information. And these three curves will approach into the channel's mutual information in the asymptotic limit, but from below. Okay. So, as a brief summary, we have studied the task of simulating a noisy channel via identity channel with non-singular resistance, and we characterize the one-shot channel simulation course under non-singular resistance as a semi-definite program. Then we introduce a channel's version of max information, which is monotone on the channel composition, and it also has the operational meaning as the one-shot quantum simulation cost. And the AEP of this new entropy is closely related to quantum reverse channel theorem. Before the end of this talk, I will mention some overall problems or outlooks. So, in our work, we only focus on the non-singularly assisted one-shot simulation course, and our start point is to use the semi-definite conditions for non-singular assistance and obtain a SDP. But if we consider the entanglement assisted scenario, the one-shot rate will be much more complicated, and we haven't obtained any good results so far. The other open problem is that can we obtain a more general form of the channel's AEP? And this has been presented by Address in Gila's workshop open problem session. So for any divergence for quantum states, we can define a channel's divergence of two quantum channels by maximizing over all the input states, and this is the worst case. So what we already know is that if the divergence is max relative entropy, and if the set Gn is the constant channel, we know this will asymptotically converge to the this is actually the channel's mutual information. And when Marshall and Werner bound actually shows that if the divergence is hypothesis relative entropy, and if this set is the constant channel, it will also converge to the channel's mutual information. Then the question is, what if we replace this set as a set containing only a single point, which is the n-fold tensor product of the channel M? So, can we obtain some similar results like quantum Slate's lemma, where the I.I.D case converge to some quantities related to the channel's relative entropy? Okay. I will stop at here. Thanks for your attention.
Thanks for your talk. We have time for several very long questions.
So, you have the max conditional mutual information. So, when the epsilon is 0, could it reduce to the mini conditional entropy?
Yes, for the two-error case, they are the same.
Could you repeat the question?
Sorry?
Could you repeat the question, please?
Oh, you mean if the the smooth max information, if epsilon equals to 0, is this entropy equal to the conditional mean entropy of the choice stage, choice matrix. So the zero error case has already studied by Duan and Winter in 2016 to show that this zero error simulation course is given by the conditional mean entropy, and our result is slightly more general. We show that if you consider the small error case, you will need the channel smooth max information, and if you take the epsilon equal to 0, it will reduce to the same quantity. So it's very compatible. Yep.
I might have missed something, but you proved as one of the main results the AEP for the smooth, for the max mutual information of channels.
Yeah.
Yeah. So that can be written as a relative entropy, right? But isn't it still open that you cannot the proof of the AEP for the max mutual information of channels, or wasn't that what Andreas and Zwiebel were trying to do?
So that's the last open question. So this quantity is actually what we define as the smooth max information of channels. So it's the distance between the channel with a set of constant channels. So this is the Imax, and what we have proved that this quantity will converge to the channel's mutual information, which is given by the channel's divergence between the quantum channel with the set of constant channels. And the open problem presented by Andreas is that if this set is only contains a single point, it's the n-fold tensor product channels.
That's still open.
Yeah, can it still hold? This is still open. So it's similar to the quantum states num, but in the channels version. And the reason why we can prove this AEP relies on the additive of this quantity. If you consider the set of constant channels, the channel's mutual information will be additive, so it will be much simpler.
Okay, so if there are no more questions, let's thank Kun again.